In this series of videos, we'll study the master method, which is a general mathematical tool for analyzing the running time of divide and conquer algorithms. We'll begin in this video motivating the method, then we'll give its formal description. That'll be followed by a video working through 6 examples. Finally, we'll conclude with 3 videos that discuss a proof of the master method, with a particular emphasis on the conceptual interpretation of the master method's 3 cases. So let me say at the outset that this lecture is a little bit more mathematical than the previous 2, but it's certainly not just math for math's sake. We'll be rewarded for our work with this powerful tool, the master method, which has a lot of predictive power. It'll give us good advice about which divide and conquer algorithms are likely to run quickly and which ones are likely to run less quickly. Indeed, it's sort of a general truism that novel algorithmic ideas often require mathematical analysis to properly evaluate. This lecture will be one example of that truism. As a motivating example, consider the computational problem of multiplying 2 n-digit numbers. Recall from our first set of lectures that we all learned the iterative grade school multiplication algorithm, and that requires a number of basic operations, additions and multiplications between single digits, which grows quadratically with the number of digits n. On the other hand, we also discussed an interesting recursive approach using the divide and conquer paradigm. So recall divide and conquer necessitates identifying smaller subproblems. So for integer multiplication, we need to identify smaller numbers that we want to multiply. So we proceeded in the obvious way, breaking each of the 2 numbers into its left half of the digits and its right half of the digits. For convenience, I'm assuming that the number of digits n is even, but it really doesn't matter. Having decomposed x and y in this way, we can now expand the product and see what we get. So let's put a box around this expression and call it star. So we began with the sort of obvious recursive algorithm where we just evaluate the expression star in the straightforward way. That is, star contains 4 products involving n over 2-digit numbers, AC, AD, BC, and BD. So we make 4 recursive calls to compute them, and then we complete the evaluation in the natural way. Namely, we append zeros as necessary and add up these 3 terms to get the final result. The way we reason about the running time of recursive algorithms like this one is using what's called a recurrence. So to introduce a recurrence, let me first make some notation, T of n. This is going to be the quantity that we really care about, the quantity that we want to upper bound. Namely, this will be the worst case number of operations that this recursive algorithm requires to multiply 2 n-digit numbers. This is exactly what we want to upper bound. A recurrence, then, is simply a way to express T of n in terms of T of smaller numbers. That is, the running time of an algorithm in terms of the work done by its recursive calls. So every recurrence has 2 ingredients. First of all, it has a base case describing the running time when there's no further recursion. And in this integer multiplication algorithm, like in most divide and conquer algorithms, the base case is easy. Once you get down to a small input, in this case 2 1-digit numbers, then the running time is just constant. All you do is multiply the 2 digits and return the result. So I'm going to express that by just declaring that T of 1, the time needed to multiply 1-digit numbers, is bounded above by a constant. I'm not going to bother to specify what this constant is. You can think of it as 1 or 2 if you like. It's not going to matter for what's to follow. The second ingredient in a recurrence is the important one, and it's what happens in the general case when you're not in the base case and you make recursive calls. And all you do is write down the running time in terms of 2 pieces. First of all, the work done by the recursive calls, and second of all, the work that's done right here now, work done outside of the recursive calls. So on the left-hand side of this general case, we just write T of n. And then we want an upper bound on T of n in terms of the work done by recursive calls and the work done outside of recursive calls. And I hope it's self-evident what the recurrence should be in this recursive algorithm for integer multiplication. As we discussed, there's exactly 4 recursive calls, and each is invoked on a pair of n over 2-digit numbers. So that gives us 4 times the time needed to multiply n over 2-digit numbers. So what do we do outside of the recursive call? Well, we pad the results of the recursive calls with a bunch of zeros, and we add them up. And I'll leave it to you to verify that grade school addition, in fact, runs in time linear in the number of digits. So putting it all together, the amount of work we do outside of the recursive calls is linear. That is, it's big O of n. Let's move on to the second, more clever recursive algorithm for integer multiplication, which dates back to Gauss. Gauss's insight was to realize that in the expression star that we're trying to evaluate, there's really only 3 fundamental quantities that we care about, the coefficients for each of the 3 terms in the expression. So this leads us to hope that perhaps we can compute these 3 quantities using only 3 recursive calls rather than 4. And indeed, we can. So what we do is we recursively compute A times C, like before, and B times D, like before, But then we compute the product of A plus B with C plus D. And the very cute fact is, if we number these three products, 1, 2, and 3, that the final quantity that we care about, the coefficient of the 10 to the n over 2 term, namely AD plus BC, is nothing more than the third product minus each of the first two. So that's the new algorithm. What's the new recurrence? The base case obviously is exactly the same as before. So the question then is, how does the general case change? And I'll let you answer this in the following quiz. So the correct response for this quiz is the second one, namely the only thing that changes with respect to the first recurrence is that the number of recursive calls drops from 4 down to 3. A couple of quick comments. So first of all, I'm being a little bit sloppy when I say there's 3 recursive calls, each on digits, each on numbers with n over 2 digits. When you take the sums a plus b and c plus d, those might well have n over 2 plus 1 digits. Amongst friends, let's ignore that. Let's just call it n over 2 digits in each of the recursive calls. As usual, the extra plus 1 is not going to matter in the final analysis. Secondly, I'm ignoring exactly what the constant factor is in the linear work done outside of the recursive calls. Indeed, it's a little bit bigger in Gauss's algorithm than it is in the naive algorithm with 4 recursive calls, but it's only by a constant factor, and that's going to be suppressed in the big O notation. So let's look at this recurrence and compare it to 2 other recurrences, one bigger, one smaller. So first of all, as we noted, it differs from the previous recurrence of the naive recursive algorithm in having 1 fewer recursive call. So we have no idea what the running time is of either of these 2 recursive algorithms, but we should be confident that this one certainly can only be better. That's for sure. Another point of contrast is merge sort. So think about what the recurrence would look like for the merge sort algorithm. It would be almost identical to this one, except instead of a 3, we'd have a 2. Right? Merge sort makes 2 recursive calls, each on an array of half the size, and outside of the recursive calls it does linear work, namely for the merge subroutine. We know the running time of merge sort, it's n log n. So this algorithm, Gauss's algorithm, is going to be worse, but we don't know by how much. So while we have a couple clues about what the running time of this algorithm might be more or less than, honestly, we have no idea what the running time of Gauss's recursive algorithm for integer multiplication really is. It is not obvious. We currently have no intuition for it. We don't know what the solution to this recurrence is, but it will be one super special case of the general master method, which we'll tackle next.